All right, in this segment, we're going to give an application of the study of spanning trees. We're going to prove that a graph is bipartite if and only if it has no odd cycle. That is, it does not contain an odd cycle as a subgraph. In this case, we're going to do proof by induction on the number of connected components of G. This proof is slightly unusual in that it turns out the inductive step is easy and it's the base case that takes the most work. So we're going to suppose first that G has at least two components, and we're going to let C be a component. So suppose G is bipartite with bipartition A and B. Then it turns out that C and G take away C are both also bipartite. As the idea is that you have some bipartition A and B. Then the point is that C goes somewhere between these two. And so if you restrict A to C and B to C, you're going to get a bipartition of C. Similarly, if you restrict the vertices of the complementary subgraphs with respect to A and B, you're also going to get a bipartition. Now, C and G take away C have fewer connected components. So by the induction hypothesis, we know that C and G take away C do not contain an odd cycle. Note that if G contained an odd cycle, it would have to be contained in one of its components. So either it'd be contained in C or G take away C, and thus we see by contradiction that G also has no odd cycle. Similarly, if G has no odd cycle, then these two subgraphs can't have odd cycles either, because if either of them did, that would also be an odd cycle in G. And so by the inductive hypothesis, C and G take away C are both bipartite graphs, with some bipartition AB and A prime B prime. Then you can check that A union A prime and B union B prime has to be a bipartition for G. Namely, if there was an edge whose endpoints were both in A and A prime, for instance, then you would see that because C is a connected component, either both endpoints would have to be in A, and thus C is not this is not a bipartition of C, or both endpoints would have to be in A prime, in which case this was not a bipartition of G take away C. So either way we cut it, we see this is a bipartition, and thus we see that for graphs with at least two components, the graph is bipartite if and only if it has no odd cycle. However, we still have to study the base case. So now G is a connected graph. We're going to negate our if and only if statement and instead show that G is not bipartite if and only if G has an odd cycle. So since G is connected, it has to have a spanning tree. Let's suppose first that G is not bipartite. And so we have to find an odd cycle, and we're going to use the spanning tree to find it. So we're going to fix some specific vertex x. And for any other vertex v in our graph, there has to be a unique path from v to x in the tree. And we're going to let d of xv be the length of that path. So d of xv is the number of vertices you have to pass in the tree to get from v to x. Note that we are restricting here to the tree. We're going to consider the following two sets. A is going to be the set of those vertices for which dxv is even, and B is going to be those vertices for which the distance between x and y is odd. Note that these have to be disjoint sets, and note that every vertex in the graph has to be in one of them. So this is a potential bipartition. But since we're assuming G is not bipartite, this is not a bipartition, so there has to be an edge in our graph where both endpoints are in one of our two sets. Given that the way this is defined, that means there has to be an edge with the property that the distance from u to x is congruent to the distance from w to x mod 2. In other words, both these numbers are even, and they're both in A, or they're both odd and they're both in B. However, by using congruence, I'm going to make the proof go a little quicker so I don't have to talk about separate cases. So we're going to let ui be the last vertex, where ui is equal to wj from some j. In other words, we have some paths going on here. A blue path from x to u and a red path from x to w. Notice that due to how the tree actually works, these parts are actually identical. even though I chose to draw them as if they were different. But for the purposes of this proof, that fact isn't needed, so I'm going to not worry about it. So UI is the last path vertex on the blue path that happens to lie on the red path. And we know there has to be at least one such vertex because X is on both. So then the point is we have an edge between U and W. So if I trace the path from U down to UI and then go along the red path and then go across, I have this cycle here. I want to claim this is an odd cycle, which means I want to claim the length of this portion of the blue path is congruent to this portion of the red path mod 2. They have the same parity so that the number of edges here adds up to an even number. So how do I do that? Well, the distance from X to U is equal to the sum of the distances from X to UI, and then from UI to U. And similarly, the distance from X to W can be separated into X to UI and then UI to W, which is this last bit here. But more importantly, because we are assuming that the distance from U to X is congruent to the distance from U to W, these two numbers these two outside numbers are congruent mod 2. And so these two summations are also congruent mod 2. And so we can cancel this part from both expressions, and we can conclude that the distance from UI to U is congruent to the distance from UI to W mod 2. In other words, both these parts are even length or odd length. Add them together, and so we see that this k minus I is congruent to m minus j mod 2. Add them together, we get an even number. Add one more edge, and we have a cycle of odd length. And thus either G was bipartite, but since we're assuming it's not, we see G has to contain an odd cycle. All right, now let's suppose G contains an odd cycle. Let's call the vertices on the odd cycle x0 through x2n. Now let's suppose we have a decomposition of V into two disjoint subsets. We want to show that A and B is not a bipartition. Up to changing the role of A and B, we can assume x0 is in A. Now suppose there exists an I less than 2n such that we have these adjacent vertices on our cycle are in B or in A. Notice here that this is designed on purpose for a reason, as we'll see in a moment. Then we already see AB can't be bipartition because then you have an edge whose endpoints are in one of the two sets. Well then, let's look at what happens. Since x0 is in A, and we're saying that x0, x1 can't both be in A, we know that x1 has to be in B. Since x1 is in B, we see that x1 and x2 can't both be in B, so x2 has to be in A. And so you start to see that every even number index vertex has to be in A, and by this condition, every odd number vertex has to be in B. In particular, that means once we reach the end of the cycle, x0 and x2n are both in A, but because this is a cycle, they're also adjacent. And so in this worst case scenario, we still found an edge whose endpoints are in one of our two sets. And thus it doesn't matter how you divide the vertices into two groups, you must contain an edge in one of them if you have an odd cycle. And therefore, if G has an odd cycle, it is not bipartite. And that ends the proof.